Welcome to Foresight's Molecular Machines Group. Really happy to be joined by Michelle Simmons today. I'll make my intro very short. She will be presenting a little longer today, which usually afterwards what I get as feedback from you guys is that if only I'd seen this one last slide a little longer. So today, hopefully you get into the full appreciation of the entire slideshow without us rushing anything. So today I will be joined by Michelle Simmons. She's the director of the Center of Excellence for Quantum Computation and Communication Technology and an Australian Research Council Laureate Fellow. So it's 7 a.m., I think, where she is. She really has pioneered unique technologies internationally to build electronic devices in silicon at the atomic scale, including the world's smallest transistor, the narrowest conducting wires, 3D atomic electronics, and the first 2-qubit gate using atom-based qubits in silicon. I'm really happy to have you here. Crucially, Michelle has also won the 2015 Foresight Feynman Prize. So very happy and honored to have you here again presenting to this group. You'll be launching into your presentation. You'll be discussing engineering qubits in silicon with atomic precision. I'll be in the chat in case people have questions. I'll be asking a few questions also that are a little bit more long-term directed in the field. But then we want to hear from all of you guys. And so thanks everyone for joining. Michelle, it's really wonderful to see you here. Thanks a lot for joining so early. And yeah, the stage is yours.
That's great. Thanks very much, Alison. Now I'm going to do my sharing screen. Well, that's interesting. Always straight away, it gives me a different thing to what we did before. Oh, one participant can share at a time. Do you know what that is?
No, I'm not sharing. So maybe
doesn't matter. I'll do that. It's giving me the same link as last time. Does that actually go straight into the presentation mode?
Yeah, this looks great.
Okay, let's hope it works. Interesting. No, it doesn't.
Sometimes you have to advance via actually clicking the keyboard.
There you go.
Yeah.
Got you.
Yeah.
Right,
Okay.
done it. Okay,
wonderful.
so thank you.
Off you go.
Thanks very much for that. Look, I've got before I start, obviously I'm a big fan of the Foresight Institute and I love the remit of it. And I've watched some of the other lectures online, which I found very exciting and interesting. So I'm a huge supporter. The title that I originally gave you was Engineering Qubits in Silicon with Atomic Precision. That's, really the lifeblood of what I do every day. But the kind of higher level thing that I believe passionately is this idea of making quantum processes by making machines at the atomic limit. So that's what really motivates me, is to really go into what Feynman originally said back in his fantastic talk in 1959. But just a few motivational slides to get us all on the same page. I think it is good to have this because I think people forget, and a lot of people will say to me, why are you trying to make things that are so small? Because it's very difficult to make them reproducible. It's never going to be commercial. The quantum world, the world at the very smallest length scales, the length scale that nature does, is not something that humans can control. And that's something that I defy, because I think it's not the case. And I look at what humankind has done over the last few years, and I just flick back between these slides because really this is the story of what mankind has been able to do. So whether it's motors, time, printers, or computers, in every case we have miniaturized them, and every time we've miniaturized them, we continue to miniaturize. We have made devices that in the olden times would be fixed devices that were enormous, that only a few people could use, such as in motors. Clocks on the edge of town halls or in stations, printers that basically allowed us to get the word out to everybody, and obviously computers. And nowadays those motors make it so that it's in nearly every kind of electronic device, whether it's a video camera or a washing machine or a Hoover or whatever else. It's now everyone has them at their disposal. Time means that we can communicate across the world because we're all synchronized. We can communicate much better with each other. Printers, young kids can now talk real time with each other, and obviously computers have allowed us to send man to the moon and solve how nature works at its fundamental limit. So all of that is driven by man's ability to control nature. And so Feynman, with his talk in 1959, I thought it was fantastic. I've taken some of the quotes out of this, and it's the kind of theme of this talk, just to bring it back to what he said, because huge visionary. He believed back in 1959 that you could manipulate atoms all the way down. And his thesis was, why do we always accept the arrangement that nature gives us? Why can't we get in there and do it ourselves? I thought that was just a fantastic insight. But that was a time when the scanning tunneling microscope, which is what my talk is going to be based on, it didn't exist then. So, it really was visionary. And his basically thesis was, we should be able to, there's nothing that stops us, the principles of physics, to get down and maneuver things atom by atom. So that's kind of just a bit of an introduction. And obviously my research is in silicon. And I just, again, just a motivation why I got into silicon atomic electronics in particular. There's two reasons. One, I was at the University of Cambridge. We were making devices in gallium arsenide, and we were literally trying to replicate the same semiconductor device twice. So, a quantum effect, such as a fractional quantum Hall effect, or one-dimensional quantization. We were trying to literally take a gallium arsenide transistor and make literally, if you make it exactly the same, do you get the same result? And we never could. And I found that unbelievably frustrating. And it was at that time that I saw a paper come out from a guy called Bruce Kane, who was actually a fellow in the US that had come to Australia for 3 years. He was at Bell Labs originally. And he basically said, the field of quantum computing was coming along theoretically. People now started to believe error correction was possible theoretically. So therefore, what's the best material to build a quantum computer in? And so for me, one of the ironies of that time is that, of course, most researchers at universities were not looking at silicon. They were looking at other materials, what was going to take over silicon. So gallium arsenide was always going to be the transistor to replace silicon. And so people were looking at, okay, what's the future materials, whether it's graphene, gallium arsenide, what other kind of new materials that are going to surpass, the might of silicon. And so nobody in the universities was looking at making small devices in silicon because the industry really owned the field in silicon. So the semiconductor industry had this massive roadmap. They were getting devices smaller and faster every year. All the technicalities of making that roadmap continue into the future basically were put out online. So a lot of industrial researchers were looking at making devices in silicon at smaller and smaller length scales, but not in the quantum regime. So the quantum regime is kind of considered too far away, unstable, never going to be commercial. So there wasn't a lot of interest in it. But of course, Moore's law was pushing things at that time to make them smaller and smaller every year. And obviously by the year 2000, 2005, we've actually crossed over. So where the actual device size is now so small, and that's a picture of a MOSFET on the right-hand side there, 22 nanometer node. The actual fin size now is below the kind of 100 nanometer level, heading down all the way now to 2 nanometers. But at that time, the quantum effect should have come into play. So they're starting to worry about literally where every atom in that transistor actually affects the threshold voltage of the transistor. So suddenly they can't make devices reproducible anymore. And they've got all kinds of problems with leakage and all kinds of, technical problems that come because the device is getting too small. And so it was that time, Bruce Kane came up with this idea. If you're going to build a quantum computer, actually silicon is the best material. It basically allows you to have a high coherence qubit, but in a nice manufacturable material itself. So you're using all the advantages of silicon, but you're making it at the smallest length scales, and you're putting an atom in and encoding the information on the electron spin on the atom. And so that's in 2000s when I moved to Australia. And the idea then was really, let's see if we can, instead of going iteratively down this line and making devices smaller and smaller as the way industry was doing, let's just jump to the technology that exists that allows you to image atoms and see if we can turn that into a manufacturing tool. So that obviously that technology is scanning tunneling microscope. And on the bottom right-hand side there is an image of a silicon surface that's been hydrogen terminated. These are 5 dimer rows of the silicon surface. It's the 100 surface. And then we've come along with the STM tip and we've removed individual hydrogen atoms to show that you can actually create this kind of atomic scale mask in silicon. And now I'm just going to go through, I'm going to do this twice. I've got 2 sets of 4 to try and give structure to the talk. And I'm going to go through and just pick out some of the things that Feynman said and show that we've actually now done that. So these were the ideas at the time. I'm going to go through those 4, and then I'm going to give you some examples, some of the recent devices that we've made. So obviously, just to remind people, the scanning tunneling microscope obviously is an ultra-high vacuum system. It requires, on bringing a tip down to the surface, it's normally a tungsten tip. You get it very close to the surface in the ultra-high vacuum, and when it's close enough, you start to get a current flowing under an applied bias. And if you keep that current constant, you can drag the tip over the atoms on the surface, and you can image the height profiles and get that kind of topographic image of what the atoms look like. So this is the silicon 100 surface that we're using. But there's a couple of things here. If we want to make atomic scale devices, number one, it's in ultra high vacuum. So whatever chemistry we have has to be compatible with an ultra high vacuum system. And number two, when you're trying to move atoms around in silicon, because they're very strongly covalently bonded, you can't just pick them up and move them around as IBM originally did with their metal atoms on a metal surface. So we knew straight away that we couldn't just pick and place atoms. We'd have to mimic essentially the lithographic process that you do through conventional silicon devices, which is normally some kind of resist that you then pattern like with optical or EVM lithography, and then basically go through layers of etching or deposition through that resist. And so back in, I guess 2000, we set up a combined ultra-high vacuum STM system, so scanning tunneling microscope with an MBE crystal growth system. And we figured out the first thing is that obviously we can see inside once you're in the microscope, you can see the atoms, but you can't see where the device is. You have to make some kind of registration marker. So we etched those registration markers into the surface. That was quite a long process to figure out how to do that. so that when you take that silicon wafer now, put it in the ultra high vacuum and take it to the high temperatures to reconstruct the surface, you can still maintain a nice crystallographic clean surface. So that took a while, but basically, and those markers have to survive, so you can find where you're patterning the device inside the UHV, and then when you take it out again. So we put the silicon in, we put a layer of hydrogen down, that's our atomic scale mask, and here we come along with our STM tip and dissolve the hydrogen from the surface, and that exposes the silicon underneath. So you can see those bright regions are the dangling bonds. You then bring in, now we're trying to build a phosphorus in silicon qubit, so we're bringing in phosphine gas as our phosphorus dopant atoms, and they will only stick to the exposed silicon, but not to the hydrogen around. And then we do what we call a controlled incorporation in the air, so we heat the surface up, phosphorus goes into that top layer, and it keeps the silicon out only in that lithographic patch, and the hydrogen resist is maintained. We then grow through the hydrogen resist with molecular beam epitaxy, so low enough temperatures that the phosphorus doesn't move. And then we can actually image it. So this isn't a tool I'll come back to image. You can do something called buried dopant imaging to show that the phosphorus has stayed in place. And obviously the deeper you go, the less clear it is, but you can actually see beneath the surface the phosphorus hasn't moved out. And then using those registration markers, you take it out of the UHV and you make contact to the device. So that's kind of like a very simple schematic of what we developed, I guess, 15 years ago now. And what we've been doing is basically making more and more complicated devices based on this. And so just to highlight, the key aspect of this is that you can make large regions where you're phosphine dosing. And when you dose with phosphine, because it's such a small molecule, you can create local metallic regions when you heat it up, or you can make wires, or you can go down to kind of like the single dopant level. So kind of the first devices that we made at that time was this kind of single electron transistor. You can see the size there, 400 nanometers. And essentially you have this small kind of funny shaped dot in the middle with the source and a drain. You apply a current through, apply bias across the source and the drain, and electrons will start to move across that dot depending on the plunge gate voltage. So your dot is quantum confined, so it's got its energy level separations. You've got your source and drain, which are essentially two-dimensional reservoirs. And so when you align the energy levels of the dot with the source and drain, you get electrons hopping through. And you can look at the conductance as a function of that, what we call in-plane gate bias. So these are all patterned on one plane. This is something I guess is contrary to the way most people see semiconductor devices. We have a kind of modulation dope structure, vertical structure. This is literally all of the conducting regions on one plane. And just by applying a bias to that in-plane gate bias, you can get electrons hop on off that central island. And then if you change the source train bias now, you can start to see all the energy levels within the dot. And that gives you what we call this beautiful Coulomb blockade or Coulomb diamonds, which allow you to measure the charging energy of the dot, which then tells you exactly the size of the dot. And so that's, when we first made these devices, they are absolutely beautifully clear. And I don't know if people have looked at other devices like this, but because the dopant atoms are sitting in substitutional sites, and because it's confined by the actual length scales of the device itself, so it's a device where the dopants literally create the potentials where the electrons can flow, you get these really strong, beautiful quantum effects. And that's really what we're trying to do, is see, can we control nature enough? Can we get in there and manipulate, put single atoms in, control single spins on atoms, and then get these kind of sensors to read them out? That was the first kind of device, and they're very reproducible. You can warm them up, cool them down, and you get the same thing every time. So that's really nice. So then the next question was, how thin can you make these leads? This is just a little schematic to show you the whole device with the etch registration markers. The gray region is the leads. The light blue is the kind of silicon encapsulation. You can make that, 1 nanometer, or you can make it hundreds of nanometers. So there's crystal grade techniques to get that nice and clean. But then it also gives you a sense of the length scale. So we can go all the way down to 1.7 nanometers with the STM. You can pattern that with respect to the markers. That takes you to the SEM, then you can see the optical microscope with the lead, and then you can get the final chip out, which then goes in a dilution fridge. You can actually measure it. So that's one thing. If we get to questions, the whole substrate has to be slightly conductive, so you can use the SEM directly. And so then when you cool them down, the substrate freezes out, and you actually just measure through the wire itself. So if we have a look at that wire now, we can see lithography basically goes along 2 dimer rows. When you dose with phosphine, like I said, it's a very small molecule, so it really crowds into that exposed silicon surface. And that basically means that the distance between the phosphorus atoms along the wire is less than the Bohr radius. So you create essentially a metallic, an extended state that runs through those wires, which is encapsulated with silicon, so it's a long way from surface states. And what we found originally was that you can make those wires all the way down to the atomic limit, and they basically maintain similar comparable resistivity to copper. So that's quite amazing. That was, to be honest, unexpected at the time. And it's because of the extremely high doping densities, because you can crowd them really, really close together. And just to put that in context, these other gray wires are freestanding wires that are heavily doped silicon with phosphorus again. But no matter how much doping they had, the mere presence of the surface basically sucks out the electrons, so that below 10 nanometers, they couldn't keep it conducting. So that having this kind of buried beneath the surface, very high doping density is really why we get that low resistivity. Now, so one of the things about I mentioned before about quantum devices is they're inherently, sensitive to noise. And so what we wanted to do is get a sense of how thin can we make the wires, and at what point do we know if we go too thin that we're going to break up into these kind of like little islands along the wire. So we've got two different wires of different thicknesses, one about 5 nanometers, one about 1.5 nanometers. And using these gates in plane, we can now look at the conductance in the wire as a function of these in-plane gate biases. And so when the wire is thick enough, that 4.6 nanometers, you can see that we're above the quantum of resistance E squared upon H. So we have this kind of very high conductance, and we are very insensitive to noise. But once we start to go below about 1.5 nanometers, those little phosphorus islands break up, and you become much more sensitive to noise. And you can actually plot the change in the conductance as a function of time for those three different locations. Above E squared upon H, it's very low noise. That's the red trace. Below E squared upon H, you're starting to see electrons hopping between the dopants along the wire, and you get these RTS signals, so you get very large noise. And so what we wanted to do then was to basically compare the noise in different physical systems to understand whether these wires would be useful for making quantum devices. If you're bringing these signals down and there's too much switching going on in the wires, it's obviously not going to help the quantum computer. And the way you can do this is you can measure the power spectral density. So that's a standard kind of measurement for measuring noise. And then you can normalize that with respect to the number of atoms in the wire to get you something called the phenomenological huge parameter. And it's the way that different people compare different physical systems. So on the right-hand side here, you can see the huge parameter for carbon nanotubes, for silicon nanowires, they're industry-based. And what you find is that these heavily phosphostate wires have these very low values of the huge parameter. So they're very low noise. And that's something, to be honest, it's still a bit of a mystery to us. But I think at the moment it's because we have these epitaxial structures with high doping density. We've got a lot of electrons that sit around there that actually screen out the noise of the dopants in them. But there's also some fundamental effect that we're still trying to investigate. So that's quite fascinating. So two-dimensional layer, half field spins, leads you to these very low noise systems. Okay, so I'm going to move on because I've got lots to tell you. The next one is the 7-atom system. So, Feynman actually had this, when we get to the small, very, very small, I'll say 7 atoms. And I think the funny thing for me is when I went back and read his talk, we actually did make a device with just 7 atoms in it. And so I just wanted to give you a sense of how it behaves now. So I showed you that large device. It had about 4,000 atoms, the SET. Now we're making the SET island really small. So you can see in the center here, you've got these kind of 6 nanometer wide wires coming in. So our source and drain. And then you've got this little tiny dot in here, which when you zoom in on the lithography, you can actually see now the green regions are the exposed silicon dimer rows on the surface. And so basically there's 2 pairs of silicon dimers, which are represented in the bottom left here as these bars. So these are basically rows of silicon atoms. And by opening up a patch size there and you dose with phosphine, you find that the phosphine likes to lose hydrogen before it can actually incorporate into the surface. So it needs space to get rid of its hydrogen. If you make that too small, so you only open up 1 hydrogen atom, the phosphine can't get in because it can't shed its hydrogen for the chemical reaction. So you have to open up a large enough space. And we spend a lot of time, maybe 3 or 4 years, looking at the chemistry of literally all the bonds that form and break to get the phosphorus to go in. And so we found that there's kind of like a rule of how many of these dimer rows you have to open up to get 1 phosphorus in. And so on this particular device, this is kind of where we started to learn this. We've got 7 phosphorus atoms have gone in to this particular device. And if you look at what we call the Coulomb diamonds on the right-hand side, this is the stability map, you see that you basically can deplete 7 electrons from the system. But now, in contrast to that last device, all the diamonds were the same height because it was a 4,000 electron system. So if you move 1 or 2 electrons, it doesn't really matter. But now when you've got such a small device, you've only got 7 on there, every time you remove an electron, you're actually physically changing the electrostatic size of the device. And so the heights of these diamonds keeps increasing as you remove electrons from the system. So that's one thing. And so 7 transitions tells us the number of phosphorus that's in there. The height of the diamonds tells us something else. But then also now we're starting to see these leads that we're making, they're 6 nanometers wide. So they're no longer these 2-dimensional reservoirs. They're actually 1-dimensional reservoirs. So you start to get these 1D density of states on either side. And that's what leads to this beautiful structure that we're seeing outside of the diamonds. So that was, again, kind of very satisfying to make a device and really start to understand literally every aspect. So all those lines tell you about the energy separation of the density of states in the leads and of the dots itself. So then, one of the things that Feynman said in his talk back in 1959 was, we can build not just individual systems, but you can start to build circuits. And that's really what we've taken to heart now. Can we build, actually not just a circuit, but can we build a whole quantum computer, a whole processor by just engineering where the phosphorus is in the system? And so I'm going to go through just a kind of sense. We've made literally hundreds of devices now. So I've had to kind of cherry pick which ones I was going to show you, but so that 100 devices really making those nanoscale sensors, actually getting to the point where we can actually put a single phosphorus in, read a single spin state. So this kind of result from 2013 is the signature of bringing a sensor nearby and measuring a spin state, looking at spin transport through the devices, looking at how you build a whole processor. So lots of theoretical work about how you'd initialize and read out individual spins in a three-dimensional architecture, which means fundamentally we can build layer by layer structures, which I'm going to show you how you can measure the wave function of the electrons on the atoms. And then all the way through now to actually demonstrating some of the measurements on qubits themselves. So showing they have very long spin relaxation times, very fast 2-qubit gates, very low noise qubits, and then basically building out these benchmarking results where by making things very small and very precise, they get closer together so they're faster. You can control the environment by putting it in this beautiful crystalline structure, so you can get rid of the noise and you can actually build these really coherent, beautiful systems. And so now we're going to go to my final 4 kind of slides of results. And that's really just to go through in a little bit more detail some of the things that I think are particularly exciting about this technology. So the first one is the single atom transistor. I've showed you 4007. Now I wanted just to go through how to get a single atom transistor. So this is a little movie about, the whole process itself to see how we go. So they take our silicon chip with those etch registration markers, put it in ultra-high vacuum, reconstruct the surface to get the silicon flat, bring our hydrogen down to form that atomic scale mask. It's actually a very nice, clean mask. Come along with that STM tip, and now we're going to open up just exactly 6 hydrogen atoms from the surface, exposing the silicon underneath. We bring the phosphine gas, it will only stick in the middle there, and it will dissociate from pH3 to 3 sets of pH2 plus hydrogen to fill that 6th hole. And then we heat the surface up so that, as I said before, it's got to get rid of its hydrogen. So a pH2 will grab a hydrogen and come off. So another pH2 will dissociate to pH. Another pH2 will grab a hydrogen and come off, so that that phosphorus atom now has got enough bare silicon that when you heat it up, it will go into the silicon and it will kick it out. And you can actually see that whole process in the STM. So it's a very beautiful thing to see. So you know where the phosphorus is because you've got the ejected silicon sitting above, which you can measure with the STM. We then get rid of the hydrogen and grow through with MBE, the silicon crystal growth. And that encapsulates the qubit in that nice environment. But at the same time, when we do that packing for the single dopant, we actually open up these leads where you see the heavily phosphorus doped silicon. So that's where those metallic leads come right down with sub-nanometer precision to where your phosphorus is. Obviously, that's all encapsulated with silicon, taken outside the UHB system. Using those markers, you make contacts to the very device. So that's kind of the very simple schematic of what you can do. But obviously, you can pattern as much as you like on those planes. So just to look at the images of the device, the top left-hand side is the actual overall structure. You can see the atomic step heights on there, and you can see the bright regions where the lithography is. And if you zoom in on that little rectangle, you can see that ejected silicon atom. So it's quite exciting. We saw that ejected silicon there. We then have to go process it in the clean room, come back and measure it at millikelvin temperatures to see, is that a phosphorus atom? And the way that you can tell that is the key thing to remember here is that when you put a phosphorus atom in silicon, the phosphorus itself has an extra nuclear spin. It creates a little Coulomb well where it sits just by its mere presence in the crystal. And that Coulomb well is sufficiently sharp, you can actually capture either 1 or 2 electrons on the system. And if it's a phosphorus atom sitting in silicon, you can optically measure it, which people did back in the 1980s, and you can work out what the energy is to get the electron between those 2 energy states, what the energy separation is between those 2 energy states. It's about 45 MeV. So that's kind of what we're looking for. If you put that in the middle here now, on the left-hand side, what we're going to do is we're going to apply a current. So you apply a voltage across the source and drain, and then change the bias on the gates G1 and G2. So there's the voltage down here. And as you apply that, again, like I showed you before, the energy level of the donor can line up with your source and drain, and you'll see these little blips in current as you can get either 1 or 2 electrons on the system. And then eventually you apply enough gate bias that you basically break down and you get tunneling across. So that's the kind of signature you'd expect. It can only hold 3 electrons, and that's exactly what we saw. And then if you measure on the right-hand side, you do this kind of stability measurement diagram again. From that Coulomb diamond, you can measure the charging energy to get 1 electron in the system, and that came out to about 47 plus or minus 2 MeV. So it basically confirmed that that was a phosphorus atom. Now that's exciting because if it was a boron atom or any other kind of atom, it would have a different charging energy. So that kind of energy tells you that it's the phosphorus atom. And we've learned lots of things about the energy. There's lines that run outside of the diamonds, and the fact that we can actually get probably more than 2 electrons. You can start, sorry, not more than 2, but you can see that that energy gap to get 2 electrons is actually bigger than we thought. So there's all kinds of things we've learned about the electrostatics of the system. Then the other really exciting thing for me, and this is probably one of the most powerful things I've seen, is that if you say to people, what does an electron look like on a phosphorus atom in silicon, you kind of have this idea of this kind of fuzzy cloud of what an electron looks like. But with the STM technique, you can actually go in once it's buried beneath the surface, and you can use the SEM technique to measure the actual wave function of the donor directly. And this is what it looks like. So it's quite a beautiful structure. And just to give you a little bit of a sense of that technique, so you're using the STM tip, you've got a conducting backgate now. And so what you're doing is you're measuring the bias between the voltage between the tip and the backgate, and electrons are tunneling from the backgate to the donor and then from the donor through the vacuum to the tip. And so in such a way, you can measure the dopant beneath the surface in a topographic mode, and it looks like there's nothing there. But then you can actually pull the tip further back, and by changing the bias on the tip, actually probe the energy levels of the actual donors themselves. And so if you do this kind of bias spectroscopy on the right-hand side here, you can see that when you get the donor energy levels aligned with the energy levels here, you get current through the device in the same way I've showed you. It's now a vertical SET rather than a lateral one. And you can park the tip at a certain bias just above where these energy levels are, and then re-image the surface and get the image of the wave function beneath the surface. This is a very nice technique, and what we've been doing over the last few years is comparing that with theoretical modeling. Because the device is now small enough, you can do atomistic modeling where you put all the atoms in directly, and you can compare what the features you see are from the measurement with what you expect from theory, and these different kind of blue and green regions tell you where the value states are in the silicon. So you're actually directly measuring where the wave function sits with respect to the orbitals and the value states within the silicon crystal. And what we found is if you literally move the atoms in different lattice locations, you get completely different signatures. So we can image an atom beneath the surface, and we can then absolutely pinpoint with lattice precision accuracy where it sits. But this is very powerful, because now if you want to bring two atoms together to do the entanglement between the qubits, you will know there are certain lattice positions where that entanglement will be nice and controllable, and other lattice positions where it's not going to be great, depending on where the wave functions sit. But that's something we're actually using to help design our qubits. It's like a tool in the background that we use to know where to put the atoms. The next device I'm going to talk about, this is a big jump, so I apologize for this. The next device is now right into a qubit structure. And because there's lots of devices that came through here, and I knew I didn't have much time, I thought I'd just try and see if I can do it in one or two slides. So now we've got on the top left-hand side here, just to put this in context, one of the things we realized is if you have two phosphorus atoms as your qubits in the structure, and you want to address one phosphorus atom, you've got to have it close enough to the other one that you can entangle them. But if they're too close and they resonate at the same frequency, then when you try and hit one, you'll hit the neighboring one. And so we realized this very early on, and there are ways that you can get around that. You can do something called Stark shifting with electric fields, but fundamentally, we thought, well, that's the error rates we generate on the two neighboring qubits is too high. But what happens if we made the qubits with different numbers of donors? So instead of one, we made one with two and one with one, and then the frequency at which they both rotate is completely different. So it's like tuning a radio, yeah? So on this particular device, I actually can't remember. It's 2p, 3p. So we've got 2p and 3p. So we've got two phosphorus in one, three phosphorus in the other. So the frequencies at which they oscillate are completely different. So they can bring them 13 nanometers apart. And now using this, again, this single electron transistor, we now bring it very close to them. So it's actually tunnel coupled. And we can, using this transistor, we can use it as a sensor to initialize on both the left and the right dot and read out the spin states of the phosphorus atoms. So that's the big jump that we've got. So we've now got this inner dilution fridge. We've got it measuring at millikelvin temperatures in a magnetic field. So you can see on the right-hand side, we split our spinned up and down energy levels for our left and right dots. And then we basically have our sensor, the SET reservoir, which is big enough now, it's more like a two-dimensional reservoir, that we bring it close. So that's the device. We've got our sensor with the SET. We've got our two donor qubits, 2p and 3p. And then we've got these gates around the outside that allow us to move the energy levels of the donors with respect to the SET island, so we can try and initialize and read out the spin. If we now look at the bottom left-hand side, we now have essentially the SET signal. And so these bright orange lines as a function of the gate bias on the left and right gate. So we're literally trying to see, can we move electrons on and off the sensor? When the sensor energy level is aligned with the qubit energy levels, we'll get breaks in these lines as electrons can move from the qubits to the sensor island in the middle here. So these bright lines running at 45 degrees, so these are just the electrons hopping off the SET as you would see before, or I showed you before. And then these breaks in the lines that you can see with the dotted white lines is when an electron, the energy level of the sensor is very close to that of the donor, and an electron can move back and forth. And if we've got it in a magnetic field on the right-hand side, you can start to see that if the spin-up energy level is above the SET island, then the electron will move off to the SET and another one will come back down, and you'll get this kind of characteristic dip in the RF-SET signal. So we're applying voltages to this. We're trying to measure where the electron spin sits. And by moving the energy levels of the dots with respect to the SET, we can tell whether we've got a spin up or spin down electron. And the exciting thing about this is you can obviously use the same sensor to measure both the left and right dots sequentially. And so if the spin is below the energy level, we'll get no signal. So we've got the first signal there shows that they're both below, so the spin downs on both must be down. The next one, we've got a spin down, spin up. Next one, spin up, spin down, and the final one, 2 spin ups. So in such a way, we can pattern this sensor with nanometer precision to where the donors are, and we can read the spin states. So we can initialize and read out the spin states on those. And that's the first kind of thing you need to do for any kind of computing architecture, is put information and read information out. But now what we want to do is we want to create a gate. So any kind of gate in a classical computer is an AND or not a NOR gate. What we're going to try and do now is a swap gate. So we're going to initialize a spin on one of the donors, initialize a spin on the other donor, bring them together using our gate biases, entangle them in the quantum world. When they get entangled, what will happen is they will naturally oscillate, and then we'll bring them back out and measure them. And so that's what we're calling that is what a swap gate is. So that's exactly what we're measuring here. So the blue signal now is where we've got the spin down up states. I've done it wrong. Spin up down states. And we're basically bringing them close together with our gate biases. They're starting to oscillate out of phase with the alternate spin states. And we can actually swap that information. And the fascinating thing about this is using this, all epitaxial, very close donor-based system, we can actually swap them within 0.8 nanoseconds. And that is super fast. So for all the qubit gates that are out there, that's the fastest you can get. And it's because they're so close, there's nothing in the way. And so you're literally just applying a small bias as a function of time. They're swapping each other around, and you can bring them back out again. So for me, this is just, it's if you told me 20 years ago that we would be able to do this, I wouldn't have known. Honestly, I wouldn't have known it. So it's absolutely fascinating that we've got to the point that we have that control now. And of course, that's hugely exciting, because what more can we do is kind of where we're going. The next result is a result that's very new. So it hasn't yet come out. It's going to come out very shortly. And this is now, can you take these atom-based systems and turn them into analog quantum simulators? So, Feynman's original idea is you can only understand nature if you can build it at the same length scale. So now we're going to literally try and see if we can build a simulator that will simulate something like a polyacetylene molecule, and see if we can work out what the lowest energy ground state is. And this is just kind of an overview slide about all the different physical systems that you can use, and to highlight when you get down to these atomic scale structures, you can bring these atoms very close together. So the distance between them is 5 nanometers, compared with kind of quantum dots, which are microns, and superconducting qubits, which are much, much bigger. And so because we've got this ability to put them where we want, we can get them very close, and that gives us these very large, what we call on-site energies. The energy to add another electron to the system is massive. The temperature scale we're working out is very small. So basically the ratio of the energy to the temperature scale puts us in what we call the truly coherent regime. This is where the quantum world wants to exist. You can really get in there without noise and temperature affecting the way that system is going to behave. And that's what you really need to understand, I think, how fundamentally how you can try and mimic nature. You've got to make it clean at the beginning. So this is now the kind of polyacetylene chain. So you've got this kind of dimerized chain. What we're now making is 2 sets of devices. They've got 10 dots in them. We've made the topological phase and the trivial phase, and the only difference between them is the separation, so the actual value of V and W. So some of them are closer together. The W is closer together on the left-hand side, and the W is further apart on the right-hand side. And so what that basically means is you've got your source and drain either side. On the one on the right-hand side, every time I add an electron to this system, it will hop on, and it will hop through, and it will come out the other side. And so when I do my kind of conductance peak again, so it's my source and drain, this is the actual picture of the device. As I add an electron to the system, I'll get a peak in the conductance that I've shown you before as a function of that gate bias. And basically they all go hopping through the chain because it's a nice, easy flow through. On the one on the left-hand side, however, we've patterned the first dot and the last dot further away from the chain. And so this is a new topological state. So what happens now is the first 4 electrons will go into the first, there'll be a barrier, nothing will happen. Eventually they'll go into these first 4 dimerized chains in the middle. Then when I get to my 5th electron, it will sit either on the left-hand side or the right-hand side. And so it will basically exist in a superposition of both of those states. As I have my 6th electron, it will lock them into that position. So the conductance will drop down a bit. And then as I have my 7th electron, it will go back to the opposite side. And so the key thing, this is a new topological state. It's called the Schriger-Heath model. It's a one-dimensional dimerized chain. It was predicted a long time ago. But basically, it shows that if you make these closer together, you get this truly coherent state where the electrons can hop from one side to the other without going through this central island. And the signature of that is you get no conductance peaks at all. So on this left-hand side, you get no conductance peaks except for 2 peaks right at the middle. And that's what's theoretically predicted, and that's exactly what we've seen. So this is exciting because it is the first time anyone's been able to do this. And just to give you a sense of, the challenge here is that you're looking at electron systems with 10 electrons with all the different interaction energies because they're so close together. And so it's actually a very physically difficult system to model using classical computing. And if you can actually build it and build these systems, you can now start to look at other topological states and going up all the way to superconductivity. So that's kind of where we're heading with this result. But the key kind of engineering challenge here are these three different things. One, we have these high on-site energies. We can pattern with sub-nanometer precision, and we have minimal gates. I'm just going to go through those. In order for this to work, all the energies of the dots have to be comparably aligned, so electrons can go through out across the other side. If they're all at different energies, then basically you don't get electron coherent transport through the chain. So then the question is, can we reproducibly make the dot size the same so that we can get the energies aligned? And there is a region where you can keep the dot size to be with the high on-site energy, but comparably the same. The second one is you have to make sure that you can literally change the distance between those donors with sub-nanometer precision. So it's really pushing below the nanometer length scale. And that allows us basically to engineer those dots further apart either end of the chain, but keep within the tunneling resistance that they can get through. And then the final one is, this is, I guess, another thing that we've learned about our system is, normally you'd think you'd have an individual gate for every dot. So 10 dots, you need 10 gates in order to control the individual energy levels to get them to line up. And then you have to also move all the energy levels up and down to see this effect. And so we've actually found out that with these epitaxial gates, because they're so skinny and small, the cross capacitance is a lot lower. So you can get rid of some of the gates. And that's something that we're still investigating. So obviously in any kind of computer architecture, you've got lots of gates coming in to control your transistors. The fewer the gates you have, the better, because you minimize the crosstalk. And this epitaxial system, because it's skinny and small, the cross capacitance is small, so you can get away with fewer gates. And I think long term, that's going to have a big impact on the kind of devices we design. So that's kind of the third result. And then the final result is just to give you a little bit of a vision of where we're going forwards. Fundamentally, any kind of computer, classical or quantum, has to be error corrected. That means that you've got to have, either in the classical world, lots of transistors running in parallel, and you compare which has the same answer. And so you have 4 or 5 different processes, and you go with the majority answer. In the quantum world, you actually have to have ancilla qubits that correct for the data qubits. So the data qubits are going to be very sensitive to phase errors. So you have ancilla qubits around them, and if you measure your qubit, you collapse it. So you can't measure them. So you have to have these ancillas that you can measure that give you information about the qubit directly. This is a whole kind of field that's called two-dimensional error correction system. And in order to do that, you need a two-dimensional grid. So you need to have these qubits around that you can independently measure, and you've got to be able to measure them in parallel and synchronously. And if you look at that, A, you've got the problem of getting connections in there, but B, because they've got to be measured in parallel and synchronously, you have to go to a three-dimensional architecture. There's no way around this, and this is true for all quantum computing schemes. And so what we have is we have our middle layer here with our grid of our phosphorus atoms with respect to an SET island that initializes and readout. But we have these control wires that now sit on 2 vertically different planes. So it's a fully three-dimensional architecture that we've been developing. And in that central layer, what we've now done is we've tried to pattern out how many can we get there, how accurately can we do that? And we've now got 1,024 of these qubits sitting in a plane with our SET island. So the STM technique, even though it's a single write process, has that precision. And that's something I think, fundamentally for any kind of processor where you're trying to replicate it, you need that precision to be able to make it the same time over and over again. So this is just a very simple result we did at the beginning. So we've now got our three different planes. So we've got in the middle plane there, we've got our red SET with a donor sitting next to it, and then we've got a vertically separated gate on the top. And so we've had to figure out how to get the crystal growth so that we can actually pattern on that top plane, having encapsulated the one underneath with enough silicon crystal that it's nice and protected. And so this is just to show you the first plane. So it showed these images of the crystal growth on that second plane, and then the lithography we can do on that. So don't forget, we're measuring a single dangling bond height on that second plane of some hundreds of nanometers of silicon growth. And so it's quite a challenge to do that. But having done that, we found that we can basically use these top gates. Again, they give these beautiful structures. And we've been able to measure a single spin with 98% fidelity on that as well. So it's it's a nice crystal structure, and there's a lot of learnings that we're getting from that. So that's kind of, I'm now going to head down to some of the final concepts that I'm going to talk about today, and that is really, so the last 20 years or so, we've taken that concept from how do you build it. We've been able to put single atoms down, get these wires connected, shown that we can build an error corrected architecture. You know where we're heading. Done this fastest 2-qubit gate, got these lowest noise systems, and very recently demonstrated that 10-dot quantum integrated circuit where we can load information in, coherently transfer across the chain and bring it out the other side. And I guess for me, the fundamental purpose of all of this is that for building a quantum computer, I think you have to be able to visualize the qubits. You have to manufacture with that precision, and then you need that control that you can literally move individual electrons and spin them around next to these sensors that you build at the atomic scale as well. So one of the advantages of the atom-based, so this is just kind of where we're heading. So we found that atom-based systems have these very long coherence times, very high control fidelities, very fast operation speeds. But the thing that I think is probably more important is the manufacturability, the fact that they have low noise, low gate densities. I haven't gone into this in any detail, but there's only 2 atoms in the actual active component of the device, phosphorus and silicon. There's nothing else there. Then the leads are far away from where the active region is. We've got this ability now to go 3D, and we're starting to look at how do you get efficient error correction. So with high quality qubits, you need fewer to correct for the errors. So that's again another kind of really exciting thing going forwards. And that really kind of brings me back a little bit to where Feynman started, to be able to see, build, and control at the quantum length scale, so that you can, and this is what he said, control the interaction of the quantized spins and embody them in a manufactured material. So he didn't say manufacturable, but can you put them in together and form these structures where you actually make machines as opposed to just individual control components. And then I'll just leave you with this. This is our kind of roadmap that we've got now. So we've looked at that classical industry, 1947, first transistor, integrated circuit, 1958, first kind of commercial product, I think it's a calculator at that time, 1964, and then at first PC, 1981. And we're basically trying to see if we can replicate that at the atomic scale. So first single atom transistor, 2012, integrated circuit, 2023, some kind of commercial processor that's going to do something useful. We don't know what that is yet. The whole world doesn't know what that is yet. So that's a big challenge for us. And then working towards error correction, because whatever happens, we've got to be able to error correct the system. And then that's it. So thank you very much for your attention.
Oh my God. Wow. Wonderful. I cannot believe this. The talk that you just gave us. Thank you so much. Maybe I'll stop sharing your screen just for a moment, but this was really, really, really fantastic. I'm so glad we had more time. Like really, really glad we had more time. I wouldn't want to have missed a single slide. My first question would have been, where will we be in 30 years? But you kind of took it away with showing the roadmap last. But maybe just to dig in a little bit in the roadmap, because you showed it so briefly. Do you want to bring us up to speed a little bit on what do you think could really be available? And I think it went to 2033. Was that the final dot on the roadmap?
Yeah, so that Alison, that's what we're hoping to do, because we've one of the great things about the silicon industry is it has this roadmap, and so they did it because they were trying to push the technology all the way through, but now it's like a roadmap for us to try and replicate and try and see what try and learn from what they learn. And I have to admit, I'm a big fan of history, so I've loved reading all of the history of those days, and had true admiration for the engineers that did it. So I guess the other thing I've learned from having read a lot of the history is they had a goal. They had to get to this goal, and they were just going to engineer the hell out of it until they got there. Nothing was going to stop them, and that's I love that approach. So for me, that's kind of what I've adopted in my team. So every day we see pretty much every device we make has some effect that we're not expecting. So there's all kinds of new things we're learning, and then we're mapping it out to build this whole kind of history of parameters about how the whole system is going to work. And then we found that obviously working with theoreticians that can mathematically model it allow us to get more predictive as we go along, because we've got enough data now that we can give them tools to help predict it. So anyway, so that's kind of the joy of the process. But so for me, it literally is, we've got we have about 4 or 5 different architectures that we're pursuing. So it's not just one. So we've got a single spin architecture, but there are many other architectures that you can pursue. So the technology is very broad, So we can make analog simulators, we can use different materials. We can make classical devices. There's a huge number of things we can do. But for us, we're very focused on building the error-corrected architecture, and that really does mean going 3D as fast as possible, and then trying to see what's the smallest logical qubit we can make, and then how we can get logical qubits working together. So there's a whole kind of roadmap for that process itself.
Is the roadmap public? Like, is it online or?
Oh no. That's so what I haven't said is we've got a company. So we built the company since 2017, and that's kind of all within the company. So, and it's really looking at all the different platform technologies, whether it's superconducting qubits or ion traps, or whatever it is, looking at the roadmaps that they're all developing, which no one's really sharing, and that, to be honest, we're making them as we go, because there's a lot of things we don't know until we get there. So it's really just building out the roadmap from current understanding. And that's, I guess, so that's why I love Feynman, because Feynman, he thought of things ahead of his time with technologies that didn't exist. And so, as a scientist, you're very normally pragmatic. You have to build with what you have. but certainly he has encouraged me, and others have encouraged me to look beyond what currently exists as to what is possible. So when we started this process, was it possible to put phosphorus in without them moving around? I didn't know. But if I looked at everything, it kind of said, well, there's a chance that it could be. And so everything we do is in that there's a chance it could be, and there's like multiple routes and multiple backups that we have in case it doesn't work. But then that mindset, we have to make it work. Doesn't matter what, if this, whatever issue comes up, we have to work around it. We have to figure out how to make it work. And that mindset, I think, has been really quite, great to have.
Wow. Yeah, we are currently also building, I guess, tech trees that are trying to get back a little bit to the roadmap, to the nanosystems roadmap that Foresight has had a while back, but actually mapping what different individuals, different labs are doing in this space. And it sounds like you just have a very, very like structured. You even have like a fallback solution. Like it sounds like I'm incredibly happy to hear that, and it's interesting that you're like stitching together different. You look at different terrains, seeing what they have, and then how you can how that will impact your roadmap. Very, very cool. So do you have any surprising applications that fell out of this, like in the next few years or something, where you're like, ooh, this could be like a new hypothesis that we want to test and like see whether that works or not?
Look, so I think the whole low noise and the quantum simulation, I think we've got a unique way of making analog quantum simulators. We're in a completely different regime. And so, there's lots of fundamental 2D materials issues that we think we can solve relatively quickly. So those first results on the simulator are really pushing us to see where we can take that technology, which is very exciting. But then, just on the fundamental side, the fact that we have these low noise structures is something to do with the fact that they're two-dimensional. And so that, again, there's kind of like just very pure fundamental physics there, as well as that kind of engineering approach that we've got. And the challenge for us is not to get too distracted by too many of the fundamentals, because I mean, I guess the thing that always motivated me is, can we understand how nature works? What is it we do and don't understand? What do we not control? So that's really,
Oh, wonderful.
sure
Is
that's your
there,
question.
usually what we often ask folks afterwards is there one specific challenge that you just really wish someone solved that would allow you to make much faster progress? That could be in your field, it could be an entirely different field. Some people, for example, say, well, I really would just love lab automation. Why is no one like really working on that? But is there something where you're just like, hey, this is a roadblock? And if this thing was solved, I would just be steaming ahead.
Yeah, I think mine is probably a little bit different to most, in that in the algorithm field of quantum algorithms, when we started, there was only a handful. Now there's 70 or so, but there's still the quantum algorithms teams tend to be too far from where the processes are out. And so this whole noisy, it's called noisy intermediate scale quantum computing. So this regime is in that situation now where we're going to have noise, and are those algorithms going to be relevant? So there's a gap between where we are with the actual devices and the actual algorithms. And for me, having algorithm people work directly with this would be something I'd love to do, so that they actually build algorithms based on the real metrics of our system, rather than the theoretical everything's perfect world. That would be probably one thing. But then, I mean, automation, a lot of groups now, including ours, are moving towards automation and bringing in machine learning. And so that's very exciting, but that's a natural evolution. But a step jump would be to get the algorithm people to work directly with the hardware guys.
Yeah,
Would be my
yeah. Software, hardware, very difficult. I think transdisciplinary collaboration ahead there, but also
Yes.
big time unlocking. So before we get into questions, Q&A with the audience, one question that I always want to ask is, what, like, let's say someone got incredibly excited about your work, hypothetically, what could they do to help your work along? Like, what's something like that? Yeah, it's just like, this is just a very shameless way to tell people how they can help this work along.
Yeah, so look, we do work. I don't know if the guys are on the line, but there's a group called company called Zyvex that have looked at, can you turn the STM into a manufacturing tool? And so are they here, Alison? I don't know. Do they come to this meeting?
I'm not sure if someone from Zyrex in the audience right now. I'll poke. No,
Okay.
I don't think so. But they'll be watching.
Yeah, so I think they're a company that have taken on a new tool, basically. So an STM was never considered a fabrication tool. We've turned it from an imaging tool to a fabrication tool. And obviously IBM back in the 90s had this idea of having 1,000 tips and automating that, which I think my understanding was that was a successful project. So in the long term, people working on those tools to turn them more into manufacturing as opposed to experimental tools would be fantastic. At the moment, we have a level of control that allows us to get to thousands of qubits. But going to millions of qubits, I think we're going to need some innovations in that technology to make it more stable and larger scale. So that would definitely be something I think is useful. And I know that that's what they're planning to do. And they're a company that's been going since 2001, I think. And so, hats off to them that they've been commercially minded all this time at a time when there was no product. Yeah. So yeah, that would definitely be something. And I think going forwards, again, something we're not going to be focusing on, but using this for different materials. So we've done it with phosphorus and silicon. I know it applies to germanium. People are starting to look at diamond and graphene. There are different dopants that you can put down. So IBM's just released a paper with a PNN junction using this kind of technique. So there's all kinds of materials that going forwards could take this way beyond just the phosphorus and silicon approach to look at different types of devices.
Wonderful. Okay, well, I'll share something once I raise here with people in the chat in case people are not familiar. And we have Steve Vedder with first audience Q&A.
Mine wasn't really a question. I was just making a few observations that tacked into other things she was saying.
Okay, wonderful. Then we'll
like an STM, she said an STM had to be in a high vacuum, and actually you can do useful stuff in a liquid with it in some cases. You get incredible electrical fields that can manipulate atoms within the, and then you can change what's in the solvent. It's tricky as heck, and I don't know if anyone has really taken it very far, but it's theoretically possible.
Well, any comment or?
No, look, I think so. I mean, just to give you a sense of, like, I agree with you. There's lots of tools out there that people pick up. I think the thing that we did was we tried to focus on one thing and take it to the limit. Yeah. And I think that dedication and, just, I don't know, bloody mindedness, for want of a better word, I think that's what you need to take these tools to the next stage. And, and at the beginning, I have to say, when we first started, the first 4 years, the yield of devices was, 10%, and it would take several weeks to get them through. So it was excruciatingly painful. But there is that fundamental belief that it could get better. That everything we did, we knew that there was all kinds of ways that we could improve it. And so now we can turn a device around in a week. It's pretty satisfying. So we've turned that tool from an imaging tool that you could spend hours every day looking at to you get the chip in there, you get it out within a day or two. It's kind of a brutal, and that's the only way this is going to work, is if you can take that tool to that limit. But yeah, I agree with you, Steve. There's a huge potential out there with these tools that is untapped.
Okay, great. Next one up, we have Steve Folks.
Fantastic presentation, and I have to say my mind is totally boggled. My question comes up about the issue of phosphorus spin state being on some level kind of an optimum choice, and it appears that it fits into the underlying crystal structure fortuitously. And I was wondering whether or not it might be useful to study, let's say, lithium, which has its lithium-6 isotope has a very, very long spin state stability, versus lithium-7 that doesn't, and therefore that contrast might be useful to investigate.
Yeah, look, I have to admit, when we started out with the phosphorus, I didn't realize just how good it was going to be. So there's lots of little things that I've learned that I'm like, oh my God, I'm so glad that worked. But yeah, I think so. Let me just answer this in many ways. So you can actually use the nuclear spins as a resource. So there's an idea of using it as a memory. It's a bit far-fetched for me, but you can actually take the electron spin, put it on the nuclear spin, bring it back. And so that's kind of exciting. And obviously, well, I haven't talked about it, but the phosphorus has to go in an isotopically pure silicon crystal. So natural silicon has 5% silicon-29, which is a spin half. So you have to isotopically purify it. So the concept of using different isotopes and different nuclear spins is something that, again, the door is just opened, and the key thing is to find what is the chemistry to get them in place. So, you can imagine these would be great materials to have, but can you actually get the chemistry to work in the tools that you have? Yeah. And so for us, the phosphorus works incredibly well. It's a gaseous dopant source. I wouldn't know what that would be for lithium, but it's something that people should investigate. Yeah? So that's my whole thing, is there would be loads of different things you could do if you could get a chemist to work on it, and then have somebody theoretically tell you what are the different isotopes that you could use and how stable they are. And then using the nuclear spins as a resource in different ways. Yeah. So So yeah, I don't know enough about lithium to answer your question, Steve, but I think it could be something people would look at for sure.
Wow, wonderful. Next one up, we have Zach.
Firstly, I think you've inspired me to look into getting a PhD, because this is incredibly fascinating. I had no idea some of these things were possible. So thank you, first off. And then my question is, do you think a reduction of the dots is kind of like a necessary step in reaching the error correcting quantum computer one day? You think so?
You mean so the dots for us or just in general? Any dot?
I would say
in general, yeah. Look, I do. So this is a fascinating conversation that's absolutely live at the moment, and that is throughout that whole process of us building this, we were always talking to industry about MOS devices, and obviously MOS devices are going to get smaller and smaller. At some point, they were going to get to the same kind of length scale, yeah, which arguably they are now, but they're still not, because the key difference is that in the MOS devices, you need an interface, so you need silicon dioxide, and you're normally putting your qubit at the interface between the two, which is where all the trap states are. So industry makes beautiful, clean interfaces. They can get their qubits there. But then when they try and get down to the last electron, their quantum dot, and they make it smaller and smaller, they need lots of gates to control the confinement potential to deplete the dots. Whereas ours comes from just the presence of the atom. So we don't need those gates. So we have a much reduced gate density because we don't need these confinement gates. But what we found is that, if you look at that wave function, if you move any kind of impurity or you move the wave function distances through the atoms, it changes the nature of the entanglement. And if you can't make the same dot that repeat it every time, then I can't see how you can control the quantum computer. You've got too much back action, too many things going on, which can concatenate as you get more and more gates in there. So for us, having these really low gate densities, very small physical systems where we control exactly where the atoms are, I think will allow us to, at some point, build systems that are much cleaner and purer for error correction than ones that have lots of gates and lots of interfaces nearby, which I think are going to stuff it up. That's my view, and history will tell. I don't know until it happens. Yeah, but
it's an incredible view, because in what I've read about Hamming error correcting codes, it's very akin to kind of the method, the sort of linear algebra sort of mindset you have to have in mapping out two-dimensional things to multi-dimensional states to effectively correct errors. And so that was my second question. Has any of the preliminary work 40 years ago been inspiration in how you've designed experiments?
So, you mean in terms of the different codes?
Yes.
Yeah, so no, I'll be honest with you, no. So, so for me, I guess it's literally been a very practical, pragmatic view. Can you make the same device twice? And what control do we have? So it's really been at that engineering length scale. And then as I've been in the field and I've read more and more about those codes and I've understood that more, then I've realized, wow, this is it. This is the way you want to be. So, but I didn't start that way. It's been a realization, and honestly, it's just because the human brain can only learn so much at one time, and all the stuff we were doing meant that I wasn't paying attention to that. And now that we're going up, and we're actually starting to run algorithms on our processors, and so then I've had to engage with higher and higher layers of the stack and understand the codes, and then I'm like, oh wow, this is even better. So that's why I think Steve asked about you learn things as you go, and unexpected wins that I'm still learning from our system.
Wonderful.
Awesome. Thank you.
Thank you so much. We're right on time, and I want to be super, super mindful of your time because we're definitely hoping to have you back and give us an update on how this is going. You've definitely blown some minds here, and thank you so, so, so much for joining us. Really, really appreciate it, and we'll be in contact with the video. I'm super.
That's great. Thanks, everyone.
Offer. Thank you.
Thanks for your time. Thanks for the questions.
Bye, everyone.
Bye.